All right, so in this video, we're just going to do a lot of practice on drawing Lewis structures. So let's just get to it. So this first one here is lithium chloride. And so for lithium chloride, uh, you might be tempted to start out and draw something like this, right? The problem is that's totally wrong. And why is that? Because got to go back to basics, some Gen Chem basics here, and remember that this is an ionic compound. We'll talk more deeply later in this chapter about identifying ionic compounds versus metallic compounds versus covalent compounds. But how do we know this? Just as a quick refresher from Gen Chem, it's because we have a metal plus a non-metal. And most of the time, that's going to give you an ionic compound. And that means that instead, we're going to have electron transfer, right, in an ionic compound, not sharing. So how do we draw the Lewis structure? Well, we start with neutral lithium, and we have fluorine, which has lithium has 1 valence electron, fluorine has 7 valence electrons. We know what's going to happen here. We're going to get electron transfer. Oops, I got to draw 7 valence electrons. 2, 4, 6, 8, 2, 4, 6, 7. We're going to have electron transfer, and that's going to end up with a lithium with no valence electrons. It's going to have the noble gas, noble configuration of helium, so it's happy. And then a fluoride with 8 valence electrons. So it's happy because it has a noble gas configuration of neon. And so that's how we draw it. You know, this just brings up a point that, you know, for ionic compounds, most of the time you're not going to be drawing Lewis structures unless you're talking about the covalent bonding within a polyatomic cation or polyatomic anion, like in ammonium. So let's do ammonium. Number of valence electrons for ammonium. Well, nitrogen is in group 5. We have hydrogen is in group 1. We have 4 of them, and so we have to multiply by 4, and then we're going to minus 1 because we have a +1 charge with a -1 electron away. That equals 8. Nitrogen is going to be the center atom. Because hydrogen always has to be a terminal atom, we'll put them all together here, stitch them together, and that's basically it. That's a positive charge. Hydrogen has the duet rule. All the hydrogens have the duet rule satisfied, and the nitrogen has the octet rule satisfied. 2, 4, 6, 8. Total number of electrons on the board, 2, 4, 6, 8 matches total number of valence electrons we have in the molecule. Next molecule is acetylene, great for making oxyacetylene torches out of, right? Burn super hot, do welding underwater, and lots of fun stuff like that. Valence electrons. Carbon, we have 2 of them, okay? So each of the carbons is worth 4, and then we have 2 hydrogens. Each of the hydrogens equal to 1. That gets us 8 plus 2 is 10 valence electrons, and we're going to have a situation. So what do? We know hydrogen is at the terminus here. There's 2 ways you could do this or start doing this. The simplest thing, you might think, well, I'm going to try to do something like this, put a carbon at the center, and then try to do something like that. And the problem is that this just doesn't really work out because in order to have carbon so the hydrogens are happy here, fine. The central carbon is happy here, right? But this carbon is not happy at all. It only has 2 electrons. So in order to make that happy, you'd have to go like that, right? And so now let's see what happens. 2, 4, 6, 8, 10, 12, 14. We're way exceeded the number of electrons. So we have too many electrons. We'd have to make a multiple bond there, right? So if we wanted to make a multiple bond and get it right from carbon's perspective, you're just going to have too many bonds on carbon now. You have more than 4 bonds, and you can never have more than 4 bonds on carbon. You can never violate the octet rule for carbon. Why? Unless you're talking about really unstable structures. Why is that? That is because carbon's in the second row of the periodic table, right? So that's not what is going to happen here. And so let me just erase all this. Okay. So instead, we know we must have a different atom connectivity, and it's going to look something like this. Sorry about that. So it's going to look something like that. So at this point, hydrogens are happy still. Okay, we have 2, 4, 6 electrons on the board. How are we going to satisfy the octet rule? Well, we'll try to put, we have 4 electrons left, right? 4 electrons left. So let's just put them down. So if we put them down, now we have 10 electrons on the board, 2, 4, 6, 8, 10. But the problem is carbon is still not satisfying the octet rule. We have 2, 4, 6 on this carbon, and this carbon is also 2, 4, 6. So that's a problem. So when we have too short number of electrons, right, we would like to do something like this, but we can't because that's too many electrons again. So we can't do that. So what do? We have to make double and triple bonds. So let's try to make a double bond. We move those electrons in. What happens? Now we look like this. Okay, and that's looking better. This carbon is still not happy because it has 2, 4, 6, not octet rule. But this carbon's happy, 2, 4, 6, 8. So what are we going to do? Well, we're going to move this electron in again, and that's going to give us a triple bond, and that's going to make our structure all in accordance with the Lewis structure rules. Hydrogen has 2. This carbon has 8, 2, 4, 6, 8. This carbon has 8, 2, 4, 6, 8. This hydrogen has 2. Total number of electrons on the board are 2, 4, 6, 8, 10. Good. Let's keep going here. Xenon Difluoride. Valence electrons here. It's going to be 8. Xenon's a noble gas, plus 7 for the halogen fluorine. And there's 2 of them, so that's going to be 22 valence electrons. We're going to have xenon difluoride. We're going to connect them, give the octet rule. Xenon is less electronegative if you look up the electronegativity of xenon, even though it is a noble gas, since it does form compounds occasionally, especially with electronegative atoms like fluorine and other halogens. It does have electronegativity. It's less electronegative than fluorine, of course, because fluorine is the most electronegative element that there is. Satisfy the octet rule. What do we have now? 2, 4, 6, 8, 10, 12, 14, 16. 16 valence electrons. We have 6 more valence electrons to put down. 2, 4, 6. We're done. But xenon is violating that octet rule. 2, 4, 6, 8, 10. But that's okay because xenon is it can't have an expanded octet because it's at or beyond period 3. You could try to make double bonds here, but that's actually going to get you worse formal charges. All right, what about chlorine trifluoride? So we have 7 for chlorine because that's a halogen. We have 7 for fluorine, that's a halogen, so 21 valence electrons. We go here and we have chlorine is the least electronegative atom, so that's going to be the central atom. Fluorine, fluorine, fluorine. Satisfy the octet rule, so we put 6 non-bonding electrons on the board for each fluorine. This has a total of 20. Oh, sorry, I did some math wrong here. There were 3 fluorines, not 2 fluorines. So that's going to bring this up to 28. Sorry about that. Anyway, so on the board here, we have 24 valence electrons. How did I do that so fast? Well, I know each fluorine has 8, 2, 4, 6, 8, and there's 3 of them. So 3 times, they're all equivalent. 3 times 8 is 24. I have 2 more lone pairs that I need to put down to get us up to 28 valence electrons. And so those are both going to go on chlorine. Similar to the xenon difluoride case, this is an expanded octet. The fluorines are happy obeying the octet rule, but the chlorine in period 3, so it can have an expanded octet, is violating the rule as 2, 4, 6, 8, 10. Last one is acetate. Valence electrons. We have 2 carbons here, so each of those is worth 4. We have 3 hydrogens, each worth 1, and we have 2 oxygens, each worth 6, and then we have a -1 charge, so we have to add 1. That's going to get us 8, plus 3 is 11, plus 12 is 23, plus 1 is 24. And how is that going to look like? It looks something like this. You know, whenever you see multiple carbons, probably you're going to have a carbon-carbon bond in it, not always, but usually this is the case with these organic type of compounds. And so you're going to have one of the carbons. Carbons are in the center, right? Because they're the least electronegative. Hydrogens can't be in the center, and oxygen's more electronegative. So you're going to have the connectivity is going to look something like this. Where are we? Hydrogens are happy. Oxygens and carbons. This carbon's happy. This carbon's not happy because it only has 2, 4, 6. This one's happy because it's 2, 4, 6, 8. Where are we total in terms of number of electrons down on the board right now? 2, 4, 6, 8, 10, 12. So we still have 12 more electrons to put down. So we only have to put down 12. We need 24 total. So we have to put down 12 more. So what do? Well, we just divide these evenly. So we're going to go 2, 4, 6, 8, 12, or as evenly as we can. Now we're all done. We have 24 electrons. We just counted those, but we have an octet rule for this oxygen 2, 4, 6, 8, but not for this one. We ran out of electrons. What do we do when we run out of electrons? We make a double bond. Okay, and so for the sake of space, I'm just going to erase this, but this lone pair I'm going to move into here. And so what is that going to do? That is going to make a double bond there. And now this carbon's also happy. Look, 2, 4, 6, 8 octet rule, and this oxygen we have a problem, right? What do we have a problem here? We only have 2, 4, 6. So let's check. What on? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. We counted them. So easy fix. Just add 2 more valence electrons. There we go. Whole thing's going to be nice, one charge. So again, octet rule satisfied here, 2, 4, 6, 8. Octet rule satisfied here, 2, 4, 6, 8. Octet satisfied for this carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. Duet rule, each of the hydrogens have 2. So, you know, the longer ones like this acetate take some time, and there's sometimes can be multiple structures. Here, you could also, equally valid resonance structure would be this, right? With basically the single bonded carbon oxygen switched with the double bonded carbon oxygen. So what does that actually tell you? It tells you that these double and single bonds really are fluxional, and that they're more accurately described as 1.5 bonds, because they're going to be an average. You're going to get an average of these 2 resonance structures. And so in this resonance structure is a single bond and a double bond here, so that's 1.5 bond average. Here was a double bond here and a single bond here, so that's also a 1.5